Again, you know, I'm all excited. Now I'm about 16, and I'm going to my first class of physics. Actually, I'm like 14 or, 15, something like that. And I'm like, oh my God, today I'm going to go into my first class of physics. I'm going to learn everything there is to know about atoms and reality. So when I sat, the first thing I did is put my hand up, and the teacher didn't know me better at the time, so he asked me what I wanted. And I said, what is an atom? I was surprised to hear the response. I thought, oh, he's just going to spell it out. What the heck is an atom? And he said, oh, that's way too complex for a first physics lesson. And in fact, we are not quite sure what an atom is. I was like, huh? You mean that in all of the years of physics that have been going on this planet, you guys still don't know what the heck is an atom? How can you tell what anything else is then? Right? And so I was like puzzled, but one thing he said is that one thing we know is that the atom is made out of 99.99999% space. And I went, oh, space. Mostly space. Everything you see, everything you touch, everything is mostly space. 99.99999%. That includes you. You are 99.99999% space. And it was like, wait a minute. That the universe is connected by a non-seen force, right? What would be the thing that would connect all things? Space. That's the only thing that's everywhere. And that's the only thing that all energy is radiated into. So I started to think, maybe it's the exact contrary. Maybe the atom is just a result of a division in space. Aha. Like the fractal structure we just saw. Divisions of space to infinity. Now it starts to look a little different, doesn't it? Is your brain starting to hurt? That's okay if it does. It's normal. Don't panic. It'll get better. But imagine you're doing music. You need silence to be able to cut it, to make music, to make a beat. If you're making reality, you need space to define the reality in between. So space, reality could be just various resolution, right? Various divisions of space in a fractal structured vacuum, which is some of the math we just published recently. It's becoming extremely popular, the concept of a structured vacuum, energetic structured vacuum. This is in advanced physics. So I dug a little bit more after that first class in physics, and I found something that blew my mind. Much later I did find it. And it says this. It's in gravitation. Present-day quantum field theory gets rid by a renormalization process of an energy density in the vacuum that would formerly be infinite, if not is not removed by renormalization. Now people, if you don't know what renormalization is, what they tried to do to me at school. It didn't work so good, can you tell? We'll talk about renormalization in a minute, but here, energy density in the vacuum that would formerly be infinite. That means that current day physics for subatomic particle, quantum physics, has to have a huge amount of energy in the vacuum for all their physics to work. Why do they try to remove it by renormalization? I'll explain that right now. There is two infinities in physics. That sounds like a misnomer, but that's the way it is. One infinity is infinitely small quantities. You know, you mix this quantity with this quantity and you approximate it, and you know, infinitely small. At one point you say, okay, well, it doesn't matter, it's just bits, you know, like infinitely small. It's okay, you can ignore infinitely small. And then there is another infinity. That one has a highly technical term that is found in physics books, and that term is nasty infinity. Yes. It's used in physics commonly. Nasty infinity is not infinitely small, but infinitely big. When you find something that's infinitely big, you can't just say, oh, I'm just going to ignore that. Right? I'm just going to ignore infinite amount of energy. I don't think so. You got to do something with it. And that's why they call it nasty, because it's like, oh my God, what do? We've got infinite amount of energy in the vacuum. You know, nobody's going to believe us. So, there's a thing in physics is that if you find nasty infinity, you got to somehow get rid of it. And if you don't, then your theory is no good. It's discarded. And the way they came up with a way to get rid of it is that they use a renormalization process. Basically, they take the infinitely large number and they cut it. Okay? And then they try to shove it under the carpet somewhere, and they don't talk about it. So, basically, you can graduate with a PhD in physics and never have heard that the vacuum density is infinite at the Planck's distance.